welcome to Math341. This is lecture 19, and we're going to be continuing with generating functions. So we'll talk a little bit more about generating functions, why they're important, and then we will talk about moment generating functions. What do you think moment generating functions give us? Moments. So you've obviously done the reading for today, right? Every now and then we have good notation in mathematics. You should not call something the moment generating function unless it gives you. Try to make sure that stays. Okay. But so every now and then we do name things well. All right. The moment generating function unfortunately does not always exist, which means you can't always use it. So we will talk a little bit about characteristic functions, which might be a little bit harder to work with, but they have the benefit of always existing. And that is a useful property to have. To try to motivate some of this time, I will talk about the change of base formula from logarithms. So I'll put in context what we're doing, that this is actually something you've seen before. So the big idea today is to try to find the right path through the algebra. There's lots of ways of doing things. This is where machine learning and artificial intelligence is just something you need to master. Because instead of just having the divine insight of the right way to look at it, it's going to try everything. And so you really need to get proficient at doing stuff like that. I'm in conversations with a lot of people as to what can we do to help students learn stuff like that. All right, just to quickly review from last time, we talked about finding the generating function for the Fibonacci numbers. I urge you to go through this calculation line by line, make sure you understand it. And we start off by just using the recurrence relation and doing a little bit of manipulations, and we get a closed form, explicit formula for the generating function. Now, if we can't do anything with it, it's useless. But if we can do something with it, we then have the hope of being able to say something about the Fibonacci numbers. And so in particular, we can try to expand it. The first thought is the denominator is 1 minus x squared. We could view this, if we wanted to, as maybe x over 1 minus r, where r is x plus x squared. We could try to expand. Unfortunately, if we try to do that, if we try to expand 1 over 1 minus x plus x squared, it would be 1 plus x squared plus x squared squared plus x squared cubed plus dot, which is 1 plus x squared. I'm going to start writing them in different colors. X plus x squared. The next one, when I square it, I'm going to get x squared plus 2x cubed plus x to the fourth. The next one, when I cube it, I'm going to get x cubed plus 3x to the fourth plus 3x to the fifth plus x to the sixth, and so on and so on and so on. And unfortunately, what we see is there's going to be multiple contributions to a power. And as we go further and further down, there's going to be more and more terms that can contribute. So I urge you to just do a few more terms and start to see if you want to find everything that's a coefficient of x to the 8th, we have to go all the way up to the 8th term, but it's not going to be just the 8th term that will contribute. The 4th term will contribute, the 5th term will contribute, the 6th term will contribute, the 7th term will contribute. The formula becomes very bad. And so the reason this is so annoying is x and x squared are of different degrees. And this leads to painful algebra. And so the better solution is to go to what is, as I remarked, usually the least favorite integration technique from calculus, right? It's the partial fractions. But if we factorize the denominator, so what we're going to do is we're going to write 1 over 1 minus x squared as 1 over 1 minus alpha x, 1 minus beta x, and then write that as a over 1 minus alpha x plus b over 1 minus beta x. You should have seen how to do this in calculus. And now when we apply the geometric series formula, it's going to be clean because you only have degree x. And so now we will get a times 1 plus alpha squared plus dot 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 plus b 1 plus beta squared. Oh, sorry, I'm forgetting the x's. X squared, x x squared plus dot dot dot. So it's going to be a plus b plus a alpha plus b beta x plus a alpha squared plus b beta squared x squared plus dot dot dot. That's our f0, that's our f1, that's our f2. And that's how we get a nice clean formula for the Fibonacci numbers. You could get a formula by doing the top method. It's just going to be a lot worse. And you could try to use that to maybe form some new kind of decomposition rules for Fibonacci numbers. One of the big things in combinatorics is if you can calculate something two different ways, then one of them becomes the theorem for the other. So if I only know, if I know two things are equivalent and I can compute one of the equivalent expressions, I now know what the second one is. So you could use this to derive more formulas for the Fibonacci's. The big point is the generating function allowed us to get a closed form expression for the Fibonacci's. We can now jump to any Fibonacci number we want. That is amazing. So we talked a little bit before about a Poisson random variable. This is one of the standard ones to look at. Poisson is nice because Poisson plus Poisson is Poisson. We've seen this with chi-squared. We've seen this with normal distributions. We see it so many times you begin to think that this is the common property. No, it's very rare to have something like this, but it's useful. It means the fundamental shape doesn't change, just the parameter value. So how did we prove Poisson plus Poisson was Poisson? So Poisson, lambda 1 plus Poisson lambda 2 was Poisson lambda 1 plus lambda 2. And we did algebra. We looked at the sum over m goes from 0 to n, the probability x1 equals m times the probability x2 equals n minus m. And that was the probability that x1 plus x2 equals n. And so we did some algebra, and at the end of the day, it worked out. It wasn't too bad algebra. We still had to do algebra. We still had to be a little bit clever. We will see, hopefully later today, another way to do this. What do you think we're going to use? What am I excited about today? Generating functions. So the whole point is applications of generating functions. Why do we care? It's going to give us another way to prove results like this. So, we've seen this before, but given a sequence an, we define the generating function to be the sum of an s to the n for all s where this converges. And in either calculus 2 or calculus 3, you hopefully saw some stuff about sequences and series. When do they converge? The comparison test, the ratio test, the root test. That's one of the reasons why that is a prerequisite for this course. If you're unsure about that material, please let me or the TAs know. Now, there is one value of s where you know the sum will converge. What is the one value of s where you know no matter what I choose for an, it's going to converge? Zero, right? So if you take s equals 0, it's clearly going to converge. Again, default, be a smartass. Look at extreme cases. Does this converge for other values of s? So one of my either favorite or least favorite functions, depending on what mood I'm in, is the exponential negative 1 over x squared. We'll say it's this: if x does not equal 0, and 0 if x equals 0. Does everybody remember Taylor series? So the Taylor series of a function is the sum, n goes from 0 to infinity, of the nth derivative at 0 over n factorial times x to the n. And of course, you don't have to do your Taylor series expansion about 0. The hope is that the Taylor series exists and converges. And if it converges, what should it converge to? So what should the Taylor series of f converge to if life were good? It should converge to f, right? It would be horrible if the Taylor series converged to a different function. Should a Taylor series be enough to uniquely specify a function. So for instance, if I say I'm thinking of a Williams student who's taking Math341 with Professor Miller, does that uniquely specify someone? No. What if I list 3 other classes? Is there anybody here who shares 4 classes with somebody this semester? So that would be enough information to uniquely specify a person. When I was a grad student, you know how they give those demographic questions at the end of the survey? There's thousands of people at Princeton, but it turns out that I was the only one who could answer the demographic questions in a certain way. And it uniquely specified me among all people. It had to do because one of the questions was, are you an undergraduate or graduate? I'm a graduate student. Are you a residential advisor or a house advisor? The house advisor was the graduate analog. There were only 2 house advisors, one myself and one a female friend of mine. And another question is, what was your gender? So by specifying gender, grad student, house advisor, it uniquely specified me. My friend Sarita was uniquely specified as well. So the question is, when do you have enough information to know that I'm thinking of this and nothing else? The hope is the Taylor series does this. If I give you the Taylor series of a function, that should be the same as giving you the function. What do you think we should calculate for this function over here? It's Taylor series, right? So this is a little bit hard to differentiate at 0. So if you, as an exercise, use L'Hopital's rule, and you will find that all the derivatives of this function at 0 are 0. Thus, the Taylor series of this function is identically 0. We will revisit this function later. It's a good exercise. I'll make it extra credit to use L'Hopital's rule to show that all the derivatives vanish at 0. It's 0 at 0. Its speed is 0. Its acceleration is 0. Its jerk is 0. And then I think I've mentioned this before. The next 3 derivatives are snap, crackle, and pop is 0. Every derivative is 0 at 0, yet this function is not identically 0. The function, the Taylor series, does converge. We are in the ridiculous situation of having a Taylor series that converges, but not to the original function, except at f equals 0, which, no offense, is really not that big of a deal, because the Taylor series starts off as f of 0 plus multiples of x, x squared, x cubed, all of which vanish at 0. They have to agree at 0. This example tells you why you need to take classes like real analysis and complex analysis. Things that seem intuitive are not. You must be careful. That's why the math side of the department, has jobs, because things like this happen, and you have to have a theory that is strong enough to tell you when do you converge to what you want to converge to. All right, so generating functions are wonderful, but we have to be careful. This Taylor series example shows us that 2 different functions could have the same Taylor series. So, sine of x and sine of x plus 1701 f of x have the same Taylor series. That's terrible. All right, so a Taylor series does not uniquely determine a function. Okay, and so now that should hopefully make us excited about this theorem. The uniqueness, and let me just kill that line. There you go. The uniqueness of generating functions of sequences. So imagine we have 2 sequences, an and bn, with generating functions g of a, g of b. So again, the notation is designed so it's easy for you to glance down and see what we're doing. I wonder what sequence g of a is associated with. And we say that these converge for all absolute value of s less than some delta. Okay? Then the 2 sequences are equal if and only if the generating functions are equal. And so we can even recover the sequences from the generating function by taking derivatives at s equals 0. I claim one direction is trivial. So if the generating functions are the same, that implies the terms are the same, or the terms being the same implies the generating function is the same? Which is the trivial direction? Knowing the terms are the same means the generating functions are the same, or knowing the generating functions are the same means the terms are the same. Yeah, knowing the terms are the same. If an equals bn, is somebody trying to get in? Could somebody open the door? Or maybe they're coming around. Okay. So if the terms are the same, then clearly the generating functions are the same because they're defined the same way, right? So one direction is trivial. The other direction is a little bit of work. So let's imagine. Okay. So proof. An equals bn trivially implies g of a of s equals gb of s. Okay, so we have that direction. We now want to look at the other direction. So for the other direction, assume ga of s equals gb of s. So we get a0 plus a1s plus dot 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 equals b0 plus b1s plus dot dot dot. And this is true for all absolute value of s less than delta. You can put in any value of s less than delta in absolute value, and you'll get this equality. What's a good value of s to 2? What choice should we take for s? There's only one natural value of s to take when I tell you it works for all s whose absolute value is less than delta. There's one canonical choice. What would make these equations really easy to evaluate? What value of s? Zero. Because if I take s equals 0, almost everything vanishes. So at s equals 0, we get a0 equals b0. Now let's study ga of s minus a0 over s, and that's going to equal gb of s minus b0 over s. Am I allowed to do that? Because a0 and b0 are the same, I could do that. If you want, instead of subtracting b0, I can subtract a0. And then this is going to imply, well, when I subtract off a and then I divide by s, I'm going to get a1 plus a2s plus dot 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 equals b1 plus b2s plus dot 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 for all absolute value of s less than delta. What value of s should I take? 0. Shampoo mathematics. Lather, rinse, repeat. It worked so well before. Take s equals 0 again. So we take s equals 0 and get a1 equals b1 and just continue. And so we can just show all the successive terms of the same. And I'll leave it to you to show that we can actually get that, an is just the nth derivative divided by n factorial. So this is very similar to Taylor's theorem. So if two generating functions are the same, then the resulting sequences that they came from are the same. That's nice. So you always want to keep in mind, does this violate anything we've seen before? Does this violate, this example exponential of -1 over x squared? Well, what am I doing here? If I'm making the Taylor series, I'm making the Taylor series from the sequence of derivatives at 0, which is the sequence of all zeros. So that would be equivalent to taking a sequence of all zeros. And then having it be the 0 function, that's the all zeros. So it's not a violation. It's just that we have multiple functions that could generate a sequence of all zeros. That's the trick. I could multiply this by 1701. I could take this to the 15th power. All of those would still work. So again, whenever you see a theorem, always ask, does this contradict something I've done before? If it does, you've made a mistake somewhere. Okay. So convolution of sequences. If we have two sequences, AN and BN, we define their convolution CK to be as follows. So CK is going to be A0 BK plus A1 BK minus 1 all the way down to AK B0. So we're just basically summing all products of A and B where the sum of the indices equals K. Does this remind you of anything? Where have you seen convolutions before? So where have we seen convolutions in this class? Yeah. And what were we doing when we were convolving two random variables? What process led to the convolution of two random variables? So we did something and it led to convolving their densities. What were we doing? So you had two variables, x and y, and convolve them came from doing what to x and y? Adding them. So adding two random variables was equivalent to convolving their density. So at this point, you should begin to see the framework of what's coming. Is anybody familiar with Chekhov's rule of literature? I've heard it phrased.
Is it like if there's a gun, it has to be fired?
Yes, if there's a gun in scene 1, it's got to be fired by scene 3. Right? You don't just plant things there to mislead. I mean, I might do that on the exams because in the real world, you often have either too little or too much information. I will always make sure you have enough information, but I might give you more information than you need. Part of your job is to figure out what matters. As soon as you start seeing things like convolution, you should be going, where else have I seen convolution in math and stats? I've seen convolution in adding independent random variables. Maybe this stuff is going to be useful for adding random variables. And so we frequently write this as A star B. And if you think about what's going on, if G of A is, A0 plus A1S plus A2S squared plus ... and G of B is B0 plus B1S plus B2S squared, and so on, what would I get if I multiplied them? So GA of S, GB of S would equal, and this is where hopefully I can just cut and paste without too much trouble. It's an interesting question as to, was this faster than just writing it again? It's more fun. Right. So if I just multiply everything out, what am I going to get? Well, I want to get the constant term, and the only way to get the constant term is to have A0 and B0 hit each other. So we'll get A0, B0. Now, how can I get a linear term? I can have A0 hit B1, or I can have A1 hit B0. So it's going to be plus A0, B1 plus A1, B0. If I want to get the cubic term, I can have A2S squared hits B0. I can have A1S hits B1S, and I can have A0 hits B2S. So that would give me an A0 B2 plus an A1 B1 plus an A2 B0 S squared, and I forgot the S over here. So if you look at this, when you expand everything out, if I have two generating functions, it's natural to multiply them together. That's a legitimate thing to do. And now I have a sequence. Well, if I call this number here C0 and C1, and C2, then this is just the generating function of the sequence C, which is what we're calling A star B. So I love to convert things to English. The log of a product is the sum of the logs, right? The derivative of a sum is the sum of the derivatives. The generating function of the quotient is the product of the generating functions. That's what we're saying. There's a nice way to understand this complicated process called convolution in terms of the simpler ones. This is what you do in chemistry and physics. You break complex things down into simple things and understand how you piece them together from the fundamental constituents. If I have two sequences A and B, I can understand this new convolved sequence in terms of each. The generating function of A star B is the generating function of A times the generating function of B. And so the next slide just formalizes that as a lemma from the book, lemma 19.4.2. So as soon as you do this, you should immediately be thinking, well, what if I had three things? And so I'm not going to spend too much time on this because we've seen this argument so many times. It's basically proof by parentheses, proof by grouping. If I have three things, A star B star C, I first look at A star B and then start that with C. And so we just go through the game, and you just have to show that convolution is associative. So all of those properties that you did in junior high, high school, is this associative or whatnot? Here's where we start to get dividends from all that. By showing convolution is associative, I can group it like this. It would be terrible if this was different than A star parentheses B star C. And I would have to worry about which way I do things. Because it's associative, it basically says it doesn't matter how you put in the parentheses. We can also reorder things. We could do A star C star B. That wouldn't matter. It's also commutative. It's very nice. It should be obvious that it has to be commutative because if it's the product of the generating functions, I can just change the order of the generating functions. So if this is true, commutativity is trivial. GA of S, GB of S is the same as GB of S, GA of S. So G A star B of S is G B star A of S. Rather than doing some tedious algebra, I can just say I can switch the order. And since these are just real numbers, when I put in a specific value of S, it doesn't matter which order I multiply them. I'm not working with matrices here. So since the order doesn't matter, if I flip the order, they've got to be the same. So GA star B is the same as GB star A. So we do have a commutative relationship. This does, oh no, I'll just do that. All right. So now let's convolve certain fun sequences. All right. Or if you don't consider them fun, at least sequences you care about because you're taking a class like Math341. All right. Does anybody recognize what AN is? What is that sequence? So basically, AL is N choose L. What's that similar to? Where have you seen this? You think of any random variables where you've seen something like this. Maybe not perfectly like this, but close. Can you give me some process where you might care about N choose L? Binomial random variable. I'm tossing a coin N times and I'm getting L heads. And maybe it's a fair coin. And that's why maybe I don't have the 1/2 to the N. So here you should be thinking binomial. And so we can define the convolution of the binomial with itself. Right? This is a very natural thing to do. It is not obscene to tell a probability distribution to go convolve yourself. Okay? So we convolve the binomial with itself. And we get the sum of N choose L, N choose N minus L. And now we've actually seen this early in the semester. We did a proof by story where we had, N students from Williams, right, and N students from Amherst, I think, and we were looking at matching things or this stuff like that. Since N choose N minus L is the same as N choose L, it's really the same as N choose L squared. The number of ways of choosing L from N is the same as the number of ways of excluding N minus L people. Hello? It's when the doctor's office calls, you always have to make sure it's not important. So we can now reprove that identity by using generating functions. So we define C to be the convolution of A with itself. So C equals A star A. So the generating function of C is just the generating function of A star A of S, which is the generating function of A times the generating function of A. And now I claim that the generating function of A is just 1 plus S to the N. So the generating function of A of S is going to be the sum, L goes from 0 to N, of N choose L S to the L. And that's just 1 plus S to the nth power. So we're just choosing our coefficients. We're choosing from AL equals N choose L for 0 less than equal to L less than equal to N. I'm choosing that to be my coefficients, and so my generating function is just the sum, AL S to the L. So it's just 1 plus S to the N. It's just the binomial theorem. If you want, you can write this as 1 to the N minus L times S to the L to make the binomial theorem a little clearer. And now we get GC of S is 1 plus S to the N times 1 plus S to the N is 1 plus S to the 2N, which is the sum K goes from 0 to 2N of 2N choose K S to the K. But this also equals over here, this is the sum K goes from 0 to 2N of C sub K S to the K. So these have to be equal. We have two generating functions. They're equal, so the individual terms must be equal. We proved that earlier today. The only way these generating functions can be the same is if they're equal term by term. If we did it one at a time, they have to have the same constant term because we just take S equals 0, so the constant terms must be the same. Subtract that, divide by S. Now the linear terms have to be the same. Subtract that, divide by S. Now the quadratic terms have to be the same. So this tells us that Cn, which is going to be the sum K goes from 0 to 2N of N choose K squared, which is coming from the sum K goes from 0 to 2N of N choose K, N choose N minus K. This has to equal the nth term over here, which is 2N choose N. So our combinatorial formula from before follows from generating functions. There's a lot you can get from generating functions. Okay, so now let's look at good generating functions. I've been saying before, take a sequence, construct the generating function. Okay, which sequences should I look at? What's the title of this class? This is probably the most marshmallow question I can ask. If you haven't spoken today, this is a slam dunk. What is the title of this class? Probability. When I was a young graduate student, I was thrilled the first day I got to proctor an exam and sit on the other side of the desk. It was an exciting moment. And with 5 minutes left in the exam, someone walked in and said, I'm sorry, I've been in the wrong room for the last 2.5 hours. I didn't realize that until now. And it was good to be the grad student, not the professor. Said, well, the professor will be here in a few minutes and I'll let him figure out what to do. So the professor comes in, goes to the student and says, okay, who's your instructor? Because there were 5 sections. I don't know. Can you describe your instructor? What do they look like? I don't know. And my brother says, you have to be able to pass the police lineup exam. If your instructor is put in a police lineup, you've got to be able to identify them. The student could not do that. Right? We need to figure out, what do we want to put in here? There's a lot of candidates. There's a tremendous number of candidates to put in for generating functions. Any sequence where the generating function converges is a good choice. This is a class on probability. Given that it's a class on probability, it makes sense that we should choose sequences related to probability. And so there's a lot of ways to choose sequences related to probabilities. Probably the simplest is to just say, hey, why don't we let AM be the probability that X equals M? Now, unfortunately, this will not always work. It's not always the case that you have a distribution that takes on integer values, or maybe we even need it to take on non-negative integer values. However, there are a lot of sequences that take on non-negative integer values. We just saw one a moment ago with the binomial distribution. Can someone give me another example? Another example of a distribution that takes on just non-negative integer values. Yeah, the Poisson, written right here. Right? What else would work? Play backgammon, Monopoly, Risk. What do all those games have in common? Dice. A discrete uniform would work. There's a lot of distributions. Negative binomial would work. There's a lot of distributions that would satisfy this. And so we can choose AM to be the probability that X equals M. Not every sequence will satisfy this. Not every probability distribution would allow us to do this, but there will be a lot that will, and this might be worth doing. And so we'll define the generating function of a random variable X to be the sum of S to the M times the probability X equals M. So this over here, this is our AM. And we can't always do this. If it takes on positive and negative values, we have to worry about convergence. If S is a small number, as M gets very large and positive, then it's going to be a very small weight. But if M is negative and S is less than 1, then it becomes a huge weight. So it becomes a little bit problematic for convergence if we have both positive and negative terms. So we often will just look at cases where we only take on non-negative values. Well, for a lot of things, that's a very reasonable assumption. How many accidents were there in the intersection? -5. No, you don't all of a sudden have 5 accidents from the previous week reverse and the cars come out fine. So we're using what's hopefully good notation. G sub X is the generating function associated to the random variable X. And if you look at what we have on the right-hand side, that's really just the expected value of S to the X. It's just the expected value of S to the X. What's the definition of that? It's S to the M times the probability X equals M. So another way of looking at generating functions is generating functions are just expected values. Here we're taking the expected value of S to the random variable. It turns out that's a good thing to do. Okay. Any questions on the definition of a probability generating function? Anybody want to compute a probability generating function? And if so, any thoughts about what we might want to try? Maybe the Poisson, right? So if we try to calculate what is the generating function of a Poisson, then that would be the expected value of S to the X that would be the sum. M goes from 0 to infinity, s to the m. And now we want the probability that it equals m. So it's going to be lambda to the m, e to the minus lambda over m factorial. All right. What could I pull outside the sum? E to the minus lambda. So we have a sum. M goes from 0 to infinity, s lambda to the m over m factorial times e to the negative lambda. And so I just did the very natural thing. I've got an s to the m right next to a lambda to the m. Why don't I just put them together? Do you recognize what that sum is? It's e to the s lambda. So this is just going to be e to the s lambda, and then we have an e to the negative lambda. So this is going to be e to the s minus 1 times lambda. So we have just calculated the probability generating function of a Poisson. Now, what if we do, let's say, xi is Poisson with parameter lambda I, then g of x1 plus x2 of s is going to be g x1 of s, g x2 of s, right? Because the sequences are convolving. So this is going to be e to the s minus 1 lambda 1, e to the s minus 1 lambda 2. This is e to the s minus 1 lambda 1 plus lambda 2. This is the probability generating function of a Poisson with parameter lambda 1 plus lambda 2. So assuming this step was correct, we just showed Poisson plus Poisson is Poisson. Assuming that you can't have two different things having the same generating function. And that's why it was so important in the beginning to prove that if we have two generating functions that are the same, then their individual terms have to be the same. And over here, the individual terms are just the probabilities. We know what the probability generating function of Poisson lambda 1 plus lambda 2 is. It's just take lambda to be lambda 1 plus lambda 2. And we've just shown if we add x1 and x2, then we get something that has the exact same generating function as Poisson lambda 1 plus lambda 2. So by all the results we have, we now know lambda 1, x1 plus x2 is Poisson lambda 1 plus lambda 2. So all the algebra we've been doing is now basically being done automatically. It's like once you calculate the rule for the derivative of x to the n, you don't have to go back to scratch to take the derivative of x to the 1701. You just use that result and say, and now take n equals 1701. We're really using facts about convolutions when we're proving results about the generating function of a sum of random variables. So we don't have to do the algebra by brute force for the sum of Poissons as we did before. We get all of this for free. Wonderful dividend. Okay, and so the big theorem, and this is what I was implicitly using a moment ago, is that if we have a bunch of independent random variables that are discrete and taking on non-negative integer values, so always be aware of what assumptions are you using. I was recently refereeing a paper where someone claimed to have proved the biggest open problem in mathematics. And I had a world expert look at it, and the world expert could not find a mistake. I looked through it line by line, could not find a mistake initially. I finally found the mistake. One of the theorems he was using was from a book where in that one chapter of the book, they assumed the Riemann hypothesis, which is what he was trying to prove. And so all of the results in that chapter were conditional on the Riemann hypothesis. So the theorem he used had as one of its hypotheses that the Riemann hypothesis is true. And using that, he was able to prove the Riemann hypothesis. And so you've got to be careful. You've got to be awake and alert. So in my other class today is going to be Peter Jones Day. He was a professor of mine at Yale. I took 3 analysis classes with him. He's the one who taught me 2 ways to do nothing. And so one of the things he always emphasized is if you take a theorem and you remove a condition, you should either be able to find a counterexample or typically the proof is a lot harder. So if we don't take on non-negative integer values, if it's not discrete, this might be false. And think about where are we using those results. And so the proof is if I have the generating function of a sum, it's just the expected value of s to the sum. Well, the expected value of s to a sum is just the expected value of the product of the s's. And then because these are independent random variables, the expected value of a product is the product of the expected values. And then each one of these is just the generating function. And then there's another way to prove it using adding as convolving and using lemma 19.4.2, which I'll just remark and leave down there. So if we have independent discrete random variables taking on non-negative integer values, the generating function of the sum is the product of the generating functions. What this means is imagine all the x's have the same density. They would all have the same generating function. And if I want to understand the sum, it's now equivalent to understanding high powers of the generating function. And maybe there's a way to do that. There is the generating function, the probability generating function. It's not the best way to do it. And this is, again, trying to find the right path through the algebra. It's a good start, but there's a better path through the algebra, which we will find in a moment. Okay, so just this slide is just to review and just make sure everybody has this emphasized. The density of the sum of independent discrete random variables is the convolution of their probabilities. This is something you just have to know and remember, extremely important. And as we've talked about, this hopefully motivates why we care so much about convolutions. Convolutions provide a tool to get to the sums. And if you want to do anything in statistics, one of the first things is going to be, I want to calculate the sample average, which means I've got to understand sums of random variables. So this is the most basic thing we can be concerned with. It is possible you might be looking at a continuous random variable rather than a discrete random variable. So this is the 21st century. I'm assuming everybody has done a search and replace at some point. When you're applying to schools and you have your personal statement, I really want to go to, well, of course, that line only works for Williams, but other things, you might search and replace and change things. And hopefully you catch all of them. They have computer programs that will now automatically send mass emails that are now personalized. And they just do a search and replace on key flags. So here, what if I have a continuous random variable? Basically, just every time you saw a sum, replace it with an integral. And the proofs follow identically. But there are some differences between continuous random variables and discrete random variables. And maybe not every result we had from discrete is going to carry over. And this is one of the reasons why earlier in the day, I started off with the function even the -1 over x squared to just alert you to how dangerous things can be. And if you think about what's going on, if I write the generating function of x is the expected value of s to the x, that makes sense whether or not I'm talking about sums or integrals. So rather than writing things and defining things in terms of sums and integrals, let me define things in terms of expected value. And then depending on what type of variable x is, it'll either be a sum or an integral. Okay. So we've done this before when we're calculating, the density of sums of continuous random variables. We have convolution defined very similarly as we did for sums. f1 star f2 is the integral of f1 of t, f2 of x minus t. If the f's are densities, then this integral will converge. It's not immediately clear that this is going to be finite. So you always want to make sure things make sense. How should I interpret what I have if the f's are densities? How should I interpret this? What is this representing? So if fi is density of xi and x1, x2 are independent, then how should I interpret f1 star f2? What is that? So how should I interpret it? It should be is the density of x1 plus x2. And if it's the density, then it has to integrate to 1. We can actually show this directly. If I integrate from minus infinity to infinity of f1 star f2 of x dx, this is the same as the integral x goes from minus infinity to infinity f. And now I put in the definition of what is f1 star f2. That's the integral t goes from minus infinity to infinity of f1 of t, f2 of x minus t, dt dx. So I first integrate with respect to t, then I integrate with respect to x. There are two things you learn in multivariable calculus. One is to change variables, and what's the other? Change the order. And so you can change the order if the integral of the absolute value is finite. Well, because my densities are non-negative, I don't have to put in absolute values. So if integral of absolute value is finite, can change order, and we're going to see what okay, we'll see what okay here. So this would be the integral t goes from minus infinity to infinity. F1 of t, integral x goes from minus infinity to infinity of f2 of x minus t dx dt. But now, what is that x integral? I'm just translating x by t. So as t, for fixed value of t, x minus t still ranges from minus infinity to infinity. This is just going to be the integral of f2, say f2 of u du. So this is just the integral from t goes from minus infinity to infinity, f1 of t dt, integral x goes from minus infinity to infinity, f2 of u du, which is 1 times 1, which is 1. So this is just a nice proof that it does converge. It should converge because we have an interpretation that it's a density. But it's nice to just be able to do the calculation as well and show. And we're using Fubini's theorem to switch the orders. So I will write that this is Fubini. Okay. So now we have a couple of big results. Sums of continuous random variables. The probability density function of a sum of independent continuous random variables is the convolution of their probability densities. So if x1 through xn have densities f1 through fn, then the density of the sum is the convolution. So we've done this when n equals 2. And then it's our standard technique, proof by grouping. So we've essentially already done this. This is just isolating it and putting it in a nice explicit form in your notes. Theorem 19.5.4, commutativity of convolution. And again, this is just extracting what we've seen before. Doesn't matter the order in which you do it. And because we have a nice interpretation, it's the density of x1 plus x2. Well, that's the same as x2 plus x1. It doesn't matter the order in which I add things. So convolution has to be commutative. You can, of course, do pages of algebra if you want. No one will stop you. No one will want to read it. All right? It's always better if you can step back and look at a high level what's going on. And at a high level, because addition is commutative, that implies that convolution is commutative. It inherits it. Okay. Now we will define moments. And so if x is a random variable with density f, its kth moment, defined in mu k with a prime, is the sum of xm to the k fxm, where we have a discrete random variable and it's taking on the values xm. Or if it's a continuous random variable, it would be the integral of x to the k times the density f of x dx. Normally, when you define things, you don't define things with a prime. So that should tell you this is really not the quantity we want to study. When we define variance, what's the notation for variance? Sigma squared. That should be telling you that's not really what we want to study. We want to study something related to that. We want to study sigma. So what's related to the moments? What's related to the moments is the centered moments, where we take the random variable x and we subtract off the mean. And then we look at the expected value of the kth power of that. So if the mean is 0, there's no difference. What we're really doing is if I have a probability distribution, let me just slide it down so that it has mean 0. That's not going to change any relative spacings or anything like that. Think of it as the negative binomial where are we counting how many tosses before we get our successes, or we're counting how many failures before we get our successes. The difference is it's not a big deal. We just need to know how to incorporate that. And so the whole point is frequently we don't care about the moments, we only care about maybe the centered moments. And then I might rescale my random variable so it has variance 1. And that's the last bit of freedom I have. I can adjust so that the mean is 0. I can adjust so that the variance is 1. And at that point, I'm out of freedom. All of these are doing, it's sending x to ax plus b. It's a nice linear transformation. And you can do this to get the mean to be 0 and the standard deviation to be 1. We can always do something like that, as long as the mean and the standard deviation are finite. And once we've done that, we can no longer do any nice linear rescaling. And we're stuck. And the moments now, the third, fourth, fifth, they start giving you the shape of the distribution. It's important to note that the first centered moment is 0. And what we're calling the first moment is really the mean mu. So mu is really mu1 prime. It's a lot of notation to write mu1 prime, so we just write mu. If the mean is 0, then the second moment, or the second centered moment, is the variance. And that occurs so often we give it a special symbol. Why do you think we use sigma for variance, sigma squared for variance? Why do you think we start with s? Isn't that a bad thing to use? The variance is sigma squared. Why are we using s? Yeah, it's because we go to the standard deviation, right? That's where the notation comes from. Think about why people chose the notation. Why do you think we use mu for mean? It's an m. Trying to just make good associations so you can look down. The worst equation I ever saw in my life was in a physics book. I don't know if I've shared this. P equals mf. Anybody want to guess what equation that was? You've all seen it. Force equals mass times acceleration. This was the worst notation I've ever seen in my life. Here. P often stands for momentum. Little f could be force or frequency. Why? Why would you do that? It's not wrong, but it makes it hard when you're looking down to see what's going on. Always think about the notation you are using. So now, what do you think the moment generating function will give us? I know I asked you this earlier. What should the moment generating function give us? The moments, right? If it doesn't give us the moment generating function, then the name sucks, right? So I'm defining the moment generating function of a random variable with density f to be the expected value of e to the tx. So if x is discrete, it's the sum. If x is continuous, it's the integral. And so the key observation is that the moment generating function of x at t is the same as the generating function at e to the t. Or equivalently, the generating function at s is the same as the moment generating function at the log of s. The whole point of this is that they're the same. We're just changing language. We're just changing normalization. We recently hosted 2 students from Argentina. One of the things that you want to know in the morning is how cold is it? And so what did I have to convert? Fahrenheit. Now I know 0 Celsius is 32 Fahrenheit, and 9 degrees of Fahrenheit is 5 degrees of Celsius. So roughly every 2 degrees of Fahrenheit above 32 is 1 degree of Celsius above 0. So I can do that to get a quick estimate and maybe round down a little bit. Not a big deal to do. If you understand Fahrenheit, you understand Celsius. You might be more comfortable having it presented in one. You give me a temperature in Celsius and I will immediately convert it to Fahrenheit so I can understand it. There's no difference between these 2 functions. You just do a change of variable, either exponentiate or take the logarithm. And it makes sense that it's exponentials and logarithms because these are the 2 functions that are inverses of each other. And the proof is just very straightforward. It's on the right. The generating function is the expected value of s to the x. So the moment generating function of s would be the expected value e to the ts, where s is equal to e to the t. And this is how we can pass back and forth between the 2 of them. So I strongly urge you to just go through and see these calculations. It's really the same as just letting s be e to the t. So now let's calculate the moment generating function of a random variable x. So it's going to be the expected value of e to the tx. So it's the integral of e to the tx f of x dx. So the first thing is to think about how might we evaluate this integral? Well, oops. So I'm integrating x goes from minus infinity to infinity. I'm putting the x on the bounds of integration to just remind myself which is the variable I'm integrating over. And now I've got to somehow do something. Let me put in the series expansion for the exponential. That's going to be the sum, n goes from 0 to infinity, of t to the n, x to the n, over n factorial, f of x dx. What should I do with the integral of the sum? The integral of the sum is the sum of the integrals. So you put on your hat that says, I'm friends with an analyst who will then justify that for you. And if we can do that, then we would get the sum, n goes from 0 to infinity. We would have a 1 over n factorial. It just was somehow overwriting something over here, but all right. So then we'll have a integral, x goes from minus infinity to infinity, x to the n, f of x dx, and then a tn over here. Okay. Can somebody tell me what that integral is? So what's the integral of x to the n times the density? Nope. It's the expected value of x to the n. So what's the expected value of x to the n? What have we called that? The nth moment, right? The hint is we're proving that this is the moment generating function. The moments need to emerge somewhere. This is the only place they can. This is just the nth moment. So we see that if we can justify the interchange, then when we calculate the moment generating function, the coefficients are the moments. Right, they're divided by n factorial, not a big deal. As long as it's a known n dependence, I can easily remove that. Or what's nice is if I take the moment generating function of x and take the nth derivative, and then take t equals 0, when I take n derivatives, the only term that will survive is the nth term. And when I take n derivatives of t to the n, that brings down an n factorial. So that's going to give me the nth moment. So this is a beautiful result. The nth derivative of the moment generating function at 0 is the nth moment. It justifies the name. This gives us another way of calculating moments. We did brute force painful calculations. We did differentiating identities. if we can calculate a closed form expression for the moment generating function, we can then just look at its Taylor series expansion and pull off the moments. This is wonderful. And then, again, the big hope to have, and I don't want to, crash your hopes, but I will, is that if you know the moments, you know the distribution. Wouldn't that be wonderful if a sequence of moments uniquely determined a distribution? Okay, so there is a bunch of properties that the moment generating function has. And these come from doing straightforward algebra. And so you should be going through the book. You should be trying to do these on your own. If you have trouble, talk to me, talk to the TAs. The first we've just done already, that the moment generating function of x is just the Taylor series expansion where the nth term is the nth moment divided by n factorial. So if we just take derivatives and set t equal to 0, we can actually recover the moments. The next is a special relationship between x and a linear rescale. We replace x with alpha x plus beta. And it tells us that the moment generating function changes in a very nice way. So the proof of that isn't too bad. It's, the moment generating function of x is the expected value of e to the tx. Let's let y equal alpha x plus beta. So the moment generating function of y is the expected value of e to the t alpha x plus beta. This is going to be the expected value of e to the t alpha x times e to the t beta. Well, e to the t beta has no x dependence, so I can pull that out. And I guess I just wrote things in the opposite order. And I have the expected value of e to the, I'll write alpha t in that order times x. That's the same as the moment generating function of x evaluated not at t, but at alpha times t. And that just gives us e to the beta t, the moment generating function at alpha t. And so what this tells us is, if you do a nice rescaling, your moment generating function changes in a very nice way. You change the argument from t to alpha t, and you have this factor e to the beta t outside. Okay, not a big deal, but this tells us if I want to change my random variables so that they have mean 0, variance 1, it's not going to change the moment generating functions in a painful way. If I replace x with x squared, all bets are off. But a simple rescale, the moment generating functions are going to be nice. All right, and then the last one is the following. So imagine we have x1 and x2 are independent random variables with moment generating functions which converge, then the moment generating function of the sum is the product of the moment generating functions. This is basically stuff we've done already. And if we just have more than 2, instead of a product of 2 terms, it's now a product of n terms. And if they're all the same, and this is the really nice part, if they're all the same, oops, hit the wrong one. If they're all the same, it becomes the moment generating function of x raised to the nth power. So if I'm summing independent, identically distributed random variables, the moment generating function of their sum is just the nth power. And maybe if things are normalized nicely, I can calculate approximately what that nth power is. And I can use 0.2 to normalize things to have mean 0, variance 1, and take into account how that goes. So what I'm trying to do here is give you some motivation as to what's coming down the pipeline. Okay. So uniqueness of moment generating functions for discrete random variables. If x and y are discrete random variables, take on non-negative integer values with moment generating functions, each converging, then they have the same distribution if and only if the moment generating functions agree up to some point. This is basically just reinterpreting a result we had before. It was a result from generating functions, but now we're applying it to moment generating functions. Well, generating and moment generating functions are equivalent either by exponentiating or taking the logarithm of the input. So if I had uniqueness before, I have uniqueness again. I don't need to do anything to prove a result like this. This page is why math is hard. I'm not going to say where these came from, but if you consider these two probability distributions, they're clearly related to each other. They're not the same. I've got the plot over here. They actually have the same moments. They even have the same half moments, but they don't have the same quarter moments. And so one of my favorite classes to teach is complex analysis. So the politically incorrect way I like to phrase it is real analysis is the democracy of mathematics. It lets every function in. And because of that, you don't have any standards. Being in doesn't mean that much. Complex analysis is the country club that's going to be sued for discriminatory practices. Complex analysis only lets very few functions in. To be real differentiable, that's not a big deal. I approach from the left, I approach from the right. Those two limits have to be the same. In complex analysis, your variable is z is x plus iy. I have to be able to approach also horizontally and vertically. I also have to be able to approach by spiraling in. I have to be able to approach by some kind of zigzag. It's so much harder to be differentiable as a complex variable that very few functions are complex differentiable. And it's a huge restriction. So it turns out if you start looking at complex moments and not just integer moments, if you have a string of moments that accumulate, say a sequence of moments m sub k, where m sub k converges to m, if they all agree, the only way that can happen is if the densities are the same. The integers don't accumulate, they're discrete. There's always a fixed separation of 1 between them. So the way you fix all this is to take complex analysis. And that's how you make all of this rigorous. So we will end today by looking at this function once again. So this is a plot. You can zoom in, and it's fun to zoom in. If you take x to be 1 over 100, this becomes e to the negative 10,000. If you take x to be 1 over 1,000, this is e to the negative 1 million. It's damn small. You know, it's really hiding how small this function is as you approach the origin. What are all the derivatives of this function at the origin? 0. This should bother you, right? I have a function. It's 0. Its derivative is 0. Its acceleration is 0. Its jerk is 0. Everything about this function is 0, and yet eventually it blows up to infinity. This shouldn't happen. What's going on here? Well, let's look at the complexification. E to the negative 1 over z squared with z equals x plus iy. Let's let x equal 0, y equal 1 over n. Then you get e to the negative 1 over I 1 over n squared. And here, I squared is negative 1. Well, this becomes e to the 1 over n squared, which is e to the n squared, which goes to infinity. So if you approach along the real axis, this function is 0. If you approach along the complex axis, this function blows up to infinity. Not only is this function not complex differentiable, it's not even complex continuous. Complex analysis will not even consider such a function like this. It's not even continuous. But real analysis, sure, come on in, we'll look at you. That's the difference between the two subjects. This is the best I can do without a 2-week digression to complex analysis as to what's going on. This hopefully just motivates why you should continue with more math theory if you really want to see what's going on. All right, so this is a good place to stop. So we will stop.